welcome to another WJEC A-level physics question. This is from Unit 1 of May 2013, and it was question 7 on the paper, and it's a question about moments and equilibrium. This question starts by asking us that, or telling us that one condition for a body to remain in equilibrium is that there should be no net moment acting on it about any point. We've got to state the other condition necessary for a body to remain in equilibrium, and this is simply that there's no resultant force in any direction. In fact, the examiners will usually just accept a simple thing like writing down sigma f equals 0, but let's write it down a bit more clearly. So, just going to say that there's no resultant force in any direction. The second part of the question, we've got a diagram showing a uniform plank of weight W pivoted so that it remains in equilibrium when two forces F1 and F2 are applied to it at distances x1 and x2 as shown, and R represents the contact force at the pivot there. The fact that it's a uniform plank tells us that the plank has got a uniform cross-sectional area, and therefore the weight labelled as W on the diagram is actually acting through the centre of the plank. Now, applying the principle of moments about the pivot, we've got to complete the equation. Well, F1 times x1 is the anti-clockwise moment that's acting on the plank. So all we need to do is write the sum of the sum of the clockwise moments. So what we've got is force W at a distance of x. So its moment will be Wx, and we got force F2, which is at a distance x2. And it doesn't matter whether we write that as F2x2 plus Wx. Then an experiment is carried out to find the weight of a physics student. We've got a uniform plank, PQ, as we can see in the diagram. It's 4 meters long and it weighs 90 newtons. And it's pivoted at about a point 0.8 meters from P. A 100 Newton weight is placed at 0.4 meters from Q in order to balance the plank horizontally. So I'm going to add a little bit extra to this diagram, if you excuse me. So I'm going to add the weight of the student down here, and we do want to find the weight of the student a little bit later on, so I'll just leave that as W. In fact, I'm just looking ahead. Yes, it is the weight that we want, not the mass. And now we've got to fill in the blanks for the missing distances here. So remember that because the plank is uniform, this weight is in the centre of the pivot. The centre of the plank. The plank is 4 meters long. So from here to here is actually 2 meters, and if this distance is 0.8 meters, then this must be 1.2 meters to give a total of 2 meters. And then various ways of working out what this middle distance is. Well, the total length is 4 meters, for example, and we've got 0.4 meters here and 0.8 meters there. So we've got to take 1.2 meters away from 4 meters, giving us 2.8 meters. There are other ways of working that out. Hence, we've got to calculate the weight of the student, and what we're really doing is using the equation that we've derived, or we wrote down in part B of the question. So the student's weight at a distance of 0.8 meters is balanced by the clockwise moments of 90 newtons at 1.2 meters. And I like to put each of these moments in a bracket just to make clear that they are separate terms. And we've also got the 100 newtons. And remember, we're looking at the distance from the pivot, so it's this 2.8 meters that we've got here. Let the calculator do the work for us, work out the right hand side and then divide it by the 0.8. Gives us a weight of 485 newtons. Then we're asked to determine the value of the force exerted by the pivot on the plank. In other words, it was that reaction force that we had in this diagram here. So if we were to add this to this diagram now, we can simply remember that the sum of the downward forces must equal the sum of the upward forces, because there must be no resultant force in any direction. So I think we called it R on the diagram. Yeah, R on the diagram is going to be equal to W plus 90 plus 100. So 485 plus 90 plus 100, which will give us 675 newtons. Then it says by taking moments about a different point Q now and using those answers that we've just worked out, confirm that the plank is in equilibrium. So if we take moments about Q, well, there's only one force that will turn this thing clockwise, which will be this force that we've just worked out, the 675 Newton reaction force. And that will be at a total distance of 3.2 meters from the pivot. On the right hand side of the equation, I'm going to put the anti-clockwise moments. We're going to have the 100 newtons at 0.4 meters. We're also going to have the 90 newtons still at 2 meters because it's still in the center. And we're going to have the student here 485 newtons at the full 4 meters. So let's evaluate the left hand side. 2160 Newton meters, and the right hand side also 2160 Newton meters. The first bracket is clearly 40, the second bracket is 180, and the third bracket, the 485 times 4, that's 1940, and you'll see that they will add up to give us that 2160. So the plank is in equilibrium. Final part of the question, the student steps off the plank. He's replaced by another heavier student who stands at point P. Which way must the pivot be moved in order to balance the plank horizontally? And then we need to explain our answer. So if we've got a heavier student here, what we've done is we've actually increased the anti-clockwise moment about this pivot. So therefore, to keep this plank in equilibrium, we either increase the clockwise moment, and we can't change these two forces, so we must change the distances, or we can reduce the moment of the heavier student by reducing his distance. Either way, what we're going to do is move the pivot towards the student, move the pivot to the left. And just put a bit of an explanation. This reduces the student's moment and increases the clockwise moments to restore equilibrium. One second, pen doesn't seem to want to write. And there we go. So once again, thank you very much for listening. Please remember to like and subscribe, and to ask any questions you like at the bottom of the page. Goodbye now.